Chapter 4, Exercise 18. Hints. Show that limit y to x f of y equals 0 for every x in R. Solution. For an integer n greater than or equal to 1, let z over n be the set of rational numbers of the form m over n, m element of integer. Note that rational numbers equals this. For any distinct points p, q in z over n, we have absolute value p minus q greater than or equal to 1 over n. We will prove that any subset A subset z over n, n greater than or equal to 1, is closed in R. By theorem 223, it is enough to prove that for any subset A subset z over n, its complement AC is open in R. We note that this. Consider a point x in AC. If x not in z over n, then x element of m over n, m plus 1 over n exclusive, for some m element of integer. Then delta equals the following. If y element of x minus delta, x plus delta exclusively, then we have the following. Consequently let this, for any point y in A, y doesn't equal x, we have absolute value y minus x greater than or equal to 1 over n. It follows that this and that. The complement AC is open in R and A is closed in R. Consider a point x in R. Sets z over n subtract x are closed. Given epsilon greater than 0, we choose an integer n greater than 1 over epsilon. By theorem 224, the union here is closed. Since this, there exists delta greater than 0 such that this. Now consider a point y in x minus delta, x plus delta exclusive, y doesn't equal x. Note that y doesn't equal 0. If y is irrational, then f of y equals 0. Assume that y in Q is of the form y equals m over k, where non-zero integers m and k do not have common divisors and k greater than 0. Since this, we have k greater than n greater than 1 over epsilon. It follows that f of y equals 1 over k less than epsilon. In any case, 0 less than or equal to f of y less than epsilon for all this. We have proved that limit y to x f of y equals 0. By definition, f of x equals 0 for irrational x and f of x greater than 0 for rational x. Consequently, the function f is continuous at every irrational point and has a simple discontinuity at every rational point. Comments. The graph of Thomai's function. The function f from this exercise is known as Thomai's function. Sets of points of continuity and points of discontinuity of Thomai's function are both dense in R. Points of discontinuity of any function g, here, is a union of a sequence of closed sets. Bayes' theorem, exercise 230, implies that there is no function g, here, which is continuous at every rational point and is discontinuous at every irrational point. Thanks for watching.